Two point two: Energy and Matter. Work and energy. We do all sorts of work in our daily lives, like when we rake leaves in the yard, move furniture, or ride our bikes. Work is done anytime an object moves while a force is applied along its direction of motion. Whenever we do work, we get hungry because we have to use energy to do work, and eating replenishes that energy. Scientists describe energy as the ability to do work. According to this description, energy is something that matter has, an ability. Just like having a wallet full of cash gives you the ability to buy things. The value of what you purchase with cash should be equivalent to the amount of money you spend. Similarly, there is an equivalence between energy and work done. In fact, scientists use the same dimensions to measure them, the Joule J. Since energy is the ability to do work, matter moves whenever work is done, and work makes changes to the energy in matter. We can see how closely connected energy and matter are. Albert Einstein made this connection even stronger with his famous equation, E equals mc squared. This equation demonstrates the equivalence of matter and energy. They are two forms of the same thing. In the beginning, God spoke everything, matter and energy, into existence. Today, we work to increase our understanding of these and other concepts to fulfill the creation mandate. Questions. What forms of energy are there? What is thermodynamics? Where did energy come from? Are heat and temperature the same? Why are there different temperature scales? Terms: energy, kinetic energy, potential energy, thermal energy, thermodynamics, law of conservation of mass energy, system, heat, temperature, exothermic process, endothermic process, Celsius scale, absolute zero, Kelvin scale, Joule. Worldview investigation, the Big Bang. You can't read much about origins in science publications without seeing a reference to the Big Bang theory, the currently accepted naturalistic theory regarding the origin of the universe. But what exactly does this theory say? There is much misinformation about what exactly the theory states and implies. Task. Your Christian school and a homeschool cooperative have been working together to produce a monthly publication. You have been asked to write an article about the Big Bang, including a perspective from a biblical worldview. Procedure. Research the Big Bang by doing an internet search using the keywords Big Bang and Big Bang cosmology. To get a biblical perspective, go to the Answers in Genesis website and search for Big Bang and Big Bang theory. Write your article, citing your sources properly. Have a classmate review your article and give you feedback. Complete your article and submit it by the deadline. Conclusion. We hear information from many sources, some reliable and others not as much. We can all fall into the trap of accepting what we have heard without doing the necessary research to verify the information. But we do a disservice to ourselves and others when we repeat incorrect information. We must be willing to seek out reliable resources and verify what we hear before we repeat information. Forms of energy. Energy is related to the force that matter generates and the resulting actions of that force. One of the most obvious forms of energy is mechanical energy. This kind of energy is commonly possessed by objects that are moving or have the potential to move. Mechanical energy is the sum of an object's kinetic energy and all forms of its potential energy. Kinetic energy, Ke, is the energy due to an object's motion, while potential energy, Pe, is the energy of an object due to its position or condition. The sum of the kinetic energy of the particles in an object is called thermal energy. We perceive the transfer of thermal energy, known as heat, as feeling hot or cold. Sound moves in waves and possesses acoustic sound energy. Some sounds are loud enough, or we could say highly energetic enough, that our skin and other organs can sense the energy, e.g., explosions. The forces that move electrically charged particles involve electrical energy. The movement of charged particles creates magnetic fields, which in turn affect other charged particles or magnetic fields. Because electricity and magnetism are so closely related, the energy associated with these two kinds of forces is called electromagnetic energy. Visible light is one form of electromagnetic energy. Energy is stored in compounds as chemical energy, a very important concept in chemistry. As chemical reactions occur, the bonds in compounds are broken, the atoms are rearranged, and new bonds form. These changes use and release chemical energy. And finally, when the nucleus of an atom breaks apart, or when particles are added to or removed from a nucleus, nuclear energy is involved. As you can see, every form of energy can change the motion of matter to do work. When energy is absorbed by matter, it has done some kind of work on that matter. More importantly, any kind of energy can be converted into another kind. Conservation of mass energy. Steam engines, like the one at right, were designed to convert energy from one form to another. In the early 19th century, scientists developed the science of thermodynamics to study the movement and conversion of energy, especially thermal energy. This new field of study began with the invention of the steam engine during the Industrial Revolution. Scientists were interested in being able to make this new invention more efficient. Scientists quickly recognized that the laws of thermodynamics seem to govern all areas of science. No exception to these laws has ever been observed in natural processes. They apply to every field at all times, in all instances. In the course of their studies, scientists discovered that in all energy conversions, energy is always conserved. In other words, in any energy conversion, the sum of all the kinds of energy produced always equals the total energy consumed. Many careful measurements have shown that energy cannot be created or destroyed, but can change from one form to another. This principle is known as the Law of Energy Conservation. We often hear references to lost energy. What is being described is the loss of useful energy. The energy in gasoline is used to move a car, but most of the energy is lost, not used to move the car, but is converted to thermal energy that leaves the car system with the exhaust. Since Einstein's equation reveals the equivalence of matter and energy, the law of energy conservation is sometimes called the law of conservation of mass energy. Matter and energy cannot be created or destroyed, but can be transformed or transferred between objects. This principle is also known as the first law of thermodynamics. Apart from instances where God created matter or energy, the total amount of mass and energy has remained constant. All mass energy changes that have occurred since creation, by natural processes or by man, have merely changed one form of energy or matter into another form of energy or matter. The first law of thermodynamics is problematic for the naturalist regarding the origins of the universe. It cannot explain the source of matter and energy from a purely naturalistic perspective. A creationist has no difficulty with this idea. Because all cause and scientific laws were brought in God, they do not contradict one another. The law of entropy. We know that water flows downhill, that warm coffee cools, and that wind blows from high pressure to low pressure. All these experiences teach us that things naturally flow from high energy states to lower energy states. Think about placing a drop of food coloring into a beaker of water. Even if you leave it undisturbed, eventually the color evenly disperses. The particles of color spread naturally from high concentration to lower concentration through a process called diffusion. You would not expect the color particles to return to form a drop-sized volume somewhere in the container. The probability of such an event is extremely remote, so remote that you would probably say that it is impossible. The measure of the dispersal of energy is called entropy. The entropy of the universe is continuously increasing as time marches on. After observing countless instances of entropy, scientists formed a conclusion. According to what is known as the second law of thermodynamics, the entropy of an isolated system can never decrease. All natural processes tend to progress toward increased entropy and toward decreased usable energy. A significant consequence of the second law of thermodynamics is that during any energy conversion, some of the energy changes into an unusable form. That is, we often say that the energy is lost. We can see the second law of thermodynamics in action in the three examples stated above. As water flows downhill, moving from high to low potential energy, some of the energy is transformed to thermal energy as the water does work on the ground over which it moves. That cup of coffee transfers thermal energy to the environment. The energy spreads throughout the room and is less usable. The pressure differential in the atmosphere produces wind that does work throughout the atmosphere, and energy is spread out. The universe is too big to study, so in order to simplify the analysis of a phenomenon, scientists will limit the scope of their investigation. They define the boundaries within which the analysis is limited. Everything inside the boundaries is called the system of interest, or just the system. A system could be a beaker in a laboratory, a rocket engine, or the entire rocket. A system can be a distinct part of an object, such as the burner of a stove. It can also be a small portion identified by imaginary boundaries within a larger volume of a substance, such as a volume of air within the atmosphere. Throughout this discussion of energy, the system is assumed to be something with distinct boundaries, an object, or a sample of a substance. Every system is subject to the second law. While work can be done on a system to increase the energy and decrease the entropy within this system, the total entropy of the system and its surroundings will still increase. Any decrease in entropy on the part of the universe comes at the expense of increased entropy elsewhere. Thermal energy, temperature, and heat. As scientists worked to understand the new field of thermodynamics, they were interested in the concept of how thermal energy moved. The term we use today for the movement or flow of thermal energy is heat, which always flows from warm to cold. The early theory of heat, that thermal energy moved as an invisible, self-repelling form of matter, was called the caloric theory. The caloric theory was workable at the time since it explained many observations about matter and thermal energy. Eventually, there were some new observations that the caloric theory could not explain, and therefore, scientists needed to modify or replace their theory. According to the particle model of matter, all matter is constructed from particles, whether atoms, molecules, or combinations of both. This model has been proposed in various forms since at least the 5th century BC. With the advances of quantitative chemistry in the early 1800s, scientists accepted the particle model of matter on experimental rather than philosophical grounds. There is strong evidence for the continuous movement of particles in matter. For example, the odor of perfume diffuses from an open bottle, and water droplets evaporate. Under a high-powered light microscope, we can see minute bits of matter moving in random ways as water particles jostle them. English botanist Robert Brown observed this in 1827. The random jiggling of microscopic matter is now known as Brownian motion. In the 19th century, thermodynamics proposed a new model for the movement of heat. Scientists agreed that particles of matter are in constant motion. At the particle level, this motion may occur in straight lines, translational motion, as small random vibrations, vibrational motion, or as a spin, rotational motion. The sum of all these motions determines the total kinetic energy of the particle. As stated previously, kinetic energy is the energy due to the motion of an object. The kinetic energy of a system is proportional to the mass of the system and the square of its velocity. The formula for kinetic energy is Ke 1/2 mv squared, where Ke is the kinetic energy in joules, m is the mass of the object in kilograms, and v is the object's velocity in meters per second. You can see that for a given particle, kinetic energy varies with velocity. Because the velocity is squared, doubling a particle's speed quadruples its kinetic energy. It is very difficult to measure the energy of each particle in a system, but we can study the energy of the entire object. As mentioned above, the thermal energy of a system is the sum of the kinetic energies of all the particles in the system. While we can measure changes to thermal energy, it is easier to measure temperature. We tend to think of temperature as a measure of how hot or cold an object is, but scientists define temperature as the average kinetic energy of the system's particles. To understand the relationship between temperature, thermal energy, and heat, consider a large pot full of hot soup. If you scoop out some of the soup to fill a small bowl, the soup in the pot and the bowl will have the same temperature because the particles have the same average kinetic energy. But the soup in the pot will have more thermal energy. This is due to the greater number of particles in the pot than in the bowl. More particles produce a greater sum of kinetic energies. As the soup sits in the bowl, it cools. The soup is transferring thermal energy to the air around it. Recall that this flow of thermal energy is called heat, and heat always moves thermal energy from a higher temperature object to an object with a lower temperature. The word heat is most correctly used as a noun, but can also be used as a verb to describe a process, such as heating a beaker. In this sense, it means to add thermal energy to something, and is the opposite of cooling, which is the removal of thermal energy. Most chemical and physical processes either release or absorb energy. These processes can be described as exergonic, releasing energy, or endergonic, absorbing energy. In thermodynamics, we are typically interested in the movement of thermal energy. Processes that release thermal energy, such as burning natural gas, the explosion of a firecracker, or the dissolving of calcium chloride, are called exothermic processes. Changes that absorb thermal energy are called endothermic processes. Chemical cold packs used to treat sprains feel cold because the chemical change absorbs thermal energy from its surroundings. We will discuss exothermic and endothermic reactions in Chapter 15, Measuring Temperature and Thermal Energy. Scientists have developed instruments to measure temperature by using thermometric properties, properties of matter that vary directly with changes in temperature. One such property is volume. In Chapter 13, you will study how the volumes of liquids and solids generally increase proportionally with temperature. If a liquid is enclosed within a thin rod of glass, a small temperature change can produce a measurable change in the distance that the liquid extends into the rod. In this instrument, called a thermometer, the change can be compared with a calibrated scale to determine the temperature. The two temperature scales used most often in chemistry are the Celsius and Kelvin scales. The Celsius scale was named in honor of Swedish astronomer Anders Celsius, who first considered making a centigrade scale, one with 100 degrees between its definition points. The Celsius scale measures temperature using the degree Celsius as its unit. Originally, the scale was calibrated to the freezing and boiling points of water. Today, the Celsius scale uses absolute zero and the triple point of water as its two reference points. These two reference points, also called fiduciary points, provide verifiable points for instrument standardization. Absolute zero is the temperature at which particles have minimum motion. Absolute zero equates to negative 273.15 degrees Celsius. The third law of thermodynamics states that we can never decrease a system's entropy to an absolute minimum. In other words, it is impossible to get any system to absolute zero. The triple point of a substance is the temperature and pressure at which the substance exists as a solid, liquid, and vapor in equilibrium. The Celsius temperature scale contains both positive and negative temperatures. While this is not a problem for observing temperatures, negative values create problems when doing calculations with the gas laws, Chapter 12. For this reason, another temperature scale was proposed in the 1800s that consisted of only positive values, called the absolute thermodynamic temperature, or Kelvin scale. The lowest possible value on the Kelvin scale is absolute zero, the point of minimum particle motion. This scale was named after the prominent Scottish physicist William Thomson, more commonly known as Lord Kelvin. A temperature change of 1 Kelvin is equal to 1 degree Celsius. The Kelvin scale uses the same two reference points as the Celsius scale and uses the Kelvin K as its unit. In 2019, both the degree Celsius and the Kelvin were redefined on the basis of the Boltzmann constant, a physical constant. As you can see from the relationships between the Kelvin and Celsius scales in Table 2.2, the numerical value of a Kelvin temperature is always 273.15 degrees more than the equivalent Celsius temperature. Kelvin temperatures are never negative, and therefore their numerical values are always greater than the corresponding Celsius temperature. This observation should help you when working on conversion problems. When required, you can make temperature measurements in degrees Celsius and then convert them to kelvins. The equations for conversion between Celsius and Kelvin temperatures are shown below. Temperature in Kelvin equals temperature in Celsius plus 273.15, and temperature in Celsius equals temperature in Kelvin minus 273.15. Tk is the Kelvin temperature, and Tc is the Celsius temperature. Note that we do not use the degree symbol when referring to Kelvin temperatures. So we say that the normal freezing point of water is 273.15 kelvins, not 273.15 degrees Kelvin. Although the Fahrenheit scale is not usually used for scientific purposes, it is the scale that most Americans know best. Use the following formula to convert from Fahrenheit to Celsius readings. Tc 5/9, Tf32. The use of a little algebra will enable you to rearrange the formula to convert Celsius temperatures into Fahrenheit temperatures. In most science applications, the standard unit of measure for work, energy, or heat in a system is the joule. The joule is named for the English physicist James Prescott Joule, who distinguished himself by his scientific integrity and his precise measurements. Another energy unit that is used less today than in the past is the calorie, cal, the amount of heat transfer required to change the temperature of 1 gram of water 1 degree Celsius. Calories and joules relate to each other according to this definition. 1 calorie equals 4.184 joules. Exactly. Larger units are called kilocalories, kcal, which are 1,000 times as large. The kilocalorie is equivalent to the calorie, note the uppercase C, which we still use in reference to the energy content of foods.